All right. Hello and welcome. Today we're going to talk about something you probably haven't thought much about since high school chemistry class, the periodic table. But we're going to look at it in a totally new way, not just as a chart, but as this incredible, powerful pharmacy for the human body.
Yeah, we all recognize this, right? But what if I told you that this chart holds the keys to treating everything from simple dehydration to complex mental illness and even cancer? Today, we're going to explore how the most basic building blocks of our universe, these individual elements, are being used as some of the most powerful medicines we have.
So before we get to all the fancy drugs, we have to start with the elements that are already inside of us, the ones that are basically running the whole show. It helps to think of your body as having its own internal electrical grid, and it's powered by some very specific, very important ions.
And the things carrying the power on this grid? Electrolytes. I know you've heard the term a million times in sports drink commercials, but this is the real science behind it. When simple mineral salts dissolve in the water in our body, they break apart into charged ions, and those ions can conduct electricity. This is quite literally the electricity of life.
So how does this grid actually work? Well, at the very heart of it is this incredible little machine, the sodium-potassium pump. This thing is a tiny engine found in almost every single one of your cells. And all it does, all day long, is push 3 sodium ions out and pull 2 potassium ions in. This one simple action creates an electrical charge across the cell membrane. It's like charging billions and billions of tiny biological batteries. And that charge is what powers every single thought you have, every nerve impulse, and every muscle contraction.
What's so crucial to understand is that each of these ions has a really specific job. Sodium, for example, mostly hangs out outside our cells, just waiting to rush in and fire off a nerve signal. Potassium, on the other hand, is mostly inside, and its job is to set up that resting electrical charge. Then you have magnesium, which is like the master multitasker inside the cell, and calcium, which is the key player in everything from flexing your bicep to building your bones.
And just to give you an idea of the scale we're talking about, let's just zoom in on magnesium for a second. It acts as a little helper molecule, a cofactor, in over 300 different enzymatic reactions inside your cells. Think about that. That's more than 300 critical processes, from creating energy to literally building your DNA that just would not happen without magnesium.
And this is where that basic biology becomes medicine. It's brilliant, really. We use magnesium hydroxide in stuff like antacids to neutralize stomach acid. And in a hospital, magnesium sulfate is given through an IV to treat really serious conditions, like a heart arrhythmia. We're literally using these essential ions that our body already needs to fix imbalances and save people's lives.
Okay, so we've seen how we use elements our body needs, but what about an element that we can introduce from the outside as a surprisingly powerful medical treatment? Well, that brings us to lithium.
Lithium is an alkali metal, sitting right next to sodium on the periodic table. But as a medicine, it is profoundly effective. For decades now, simple lithium salts have been the absolute cornerstone treatment for bipolar disorder. It works by stabilizing mood, and, incredibly, it significantly reduces the risk of suicide in patients. It's a lifesaver.
But here is the massive catch. Using lithium is a very, very delicate balancing act. On the one hand, it's this life-changing, life-saving mood stabilizer. But on the other hand, the line between a dose that helps and a dose that harms is incredibly, dangerously thin. This is what doctors call a narrow therapeutic window.
And when I say thin, I mean razor thin. A good therapeutic level of lithium in the blood is usually somewhere between 0.4 and 1.0 millimoles per liter. But if you push it just past 1.5, you start hitting toxic levels that can cause tremors and damage the kidneys. And if it gets above 2.0, it can actually be fatal. This is exactly why patients who take lithium need constant, careful monitoring.
So, we've seen how we use elements our bodies need and how we use simple elemental salts as powerful drugs. Now for the really futuristic part. What if we could actually rebuild the drugs we already have, atom by atom, to make them even better? This is the core idea behind a brilliant strategy called the carbon-silicon switch, and it's pretty much what it sounds like. Chemists take a drug molecule that's built on a carbon backbone, which is most of them, and they strategically swap out just one carbon atom for a silicon atom. It sounds like such a tiny change, but it can have absolutely massive consequences for how the drug works.
So why does this even work? Well, if you look at the periodic table, carbon and silicon are in the same group. They're like chemical cousins. They have similar basic chemistry, but they also have some key differences. Silicon atoms are bigger, so they make longer, more flexible bonds.
They're also less electronegative, which changes the electrical properties of the bond. And here's the big one. They tend to make molecules more lipophilic, meaning more soluble in fat. This can completely change how a drug gets absorbed and used by the body.
Okay, let's look at a real-world example to make this clear. On the left, we've got indomethacin, a pretty standard anti-inflammatory drug. And on the right, that's its silicon analog, where chemists have performed that one tiny switch. They look almost identical, but that single silicon atom, tucked away in the structure, changes everything.
So the original drug, it just reduces inflammation. But this new silicon version, it's being investigated as an anti-cancer agent. And get this, in lab tests against pancreatic cancer cells, it showed a 15-fold increase in its ability to stop those cells from growing. 15 times better. That single atom switch completely repurposed the drug for a brand new, incredibly powerful effect.
And this isn't a one-off trick. Here's another amazing case. This molecule is called haloperidol. It's a silicone-based version of haloperidol, which is an older but still effective antipsychotic drug used to treat schizophrenia.
Now, the original drug works, but one of its biggest problems is that it can cause some really severe movement-related side effects. So researchers tried to switch. They swapped a key carbon atom for silicon, and the result, haloperidol, was found to be significantly more potent. And the hope here is that a more potent drug could be used at a much lower dose, which could potentially reduce or even eliminate those debilitating side effects. It's a huge deal.
Okay, so what's the big picture here? What's the main takeaway from this whole journey across the periodic table? Let's pull all these threads together.
Think about the story we just told. We started with the absolute foundation of our biology, those essential ions that form our body's electrical grid. Then we moved to direct intervention, where we use a simple element like lithium to manage a really complex mental health condition. And we ended up at the cutting edge of innovation, where chemists are literally rebuilding medicines one atom at a time to make them safer, better, and more effective.
It really makes you think, doesn't it? The same exact elements that make up the salt on our dinner table and the computer chips in our phones are also the fundamental ingredients in the pharmacy of the future. The periodic table isn't just some chart on a classroom wall, it's a treasure map, and we're still just beginning to discover all the secrets it holds. It really makes you wonder, what new therapies are we going to unlock next?